lottery. When Minnesotans play the lottery, the proceeds or the funds from that, whether they win or lose, go into a pot, and a portion of that pot of lottery proceeds is designated for the Environment and Natural Resources Trust Fund. And then state organizations like the Minnesota Geological Survey, the DNR, other groups compete for that money to undertake projects that help protect and enhance our environmental resources. So MGS and DNR are beneficiaries of that, and that's where all of the funding comes from, which is just kind of cool. You can see our progress map here on the lower right. All of the counties in deep red are counties that have Part A atlases done. Green are underway. Orange are some combination of the two. And then the gray counties there are the only ones we haven't started yet. Nick will show you the map of the DNR status for progress, and they'll have a few less counties filled in simply because they have to wait for us to get our stuff done before they can start their stuff. This is just kind of a visual representation of the different plates and what they're talking about. Okay, so right here, plate 3, that's the superficial geology. We're talking about the quaternary sediment, the till and the clay and the sand and gravel right at the surface. Plate 2, on the other hand, talks about the bedrock, everything that's buried under all the sediment. Plate 5 talks about what's between the ground surface and the bedrock surface. And plate 6 talks about the shape of that bedrock surface. Here's what the full atlas for Hubbard County looks like. As I said, it's 6 different plates laid out. And we'll go through these one by one. But they all have the exact same footprint and layout. So you can kind of like put them next to each other if you need to reference one and see where a contact is on one and where a unit is on another. And of course, I also should mention, we do print these physically, so you can have the big maps to drive around the county with if you want, but everything is also, of course, made digital and all available free. What we do is map at a 1 to 24,000 scale, and that's like a quadrangle scale. If you've seen like the green and blue topo maps from the DNR, those are 1 to 24,000 scale. Our maps are printed at 1 to 100,000 scale, just because the counties are so big that you couldn't print something at 1 to 24,000 scale. But that's the detail at which we map it. And there are a ton of associated databases that go with this. It's not just the maps that are produced. You're also getting access to the data that the geologists use to make the maps. And that includes everything from water wells, scientific drilling records, sediment samples, bedrock outcrops, if there were any, which there are not here, and a bunch of geophysical imagery as well. And we try to make it really explicit when we write the text for these plates, which data we use in which place to help us figure out what the map units are. We also have a user's guide available online, and I will show you where all of this is now. What you want to do is go to cse.umn.edu/MGS, CSE for College of Science and Engineering, UMN because we're a part of the University of Minnesota, .edu/MGS for Minnesota Geological Survey. If you wanted to find the Hubbard Atlas online, you would first click over here under Data and Mapping Programs. A drop-down menu will appear, and you'll click on the County Geologic Atlas tab. It'll bring up this map that I just showed you. Now this image is a little bit out of date, but you just go and click on the county that you want. As long as it's a county that's done, you'll be able to access the information. Once you click on a county, it'll pop up this table, letting you know what county it is, what the publication number is, and giving you a link to the data itself. Once you click on a certain county, say for example, Hubbard, it takes you to a screen dedicated just to the Hubbard County Atlas. And on the side over here in this menu, you can download each of the plates individually. So if you just wanted to print the quaternary stratigraphy, you could do that. Can't really print it on like an 8.5 by 11 printer, but if you had a plotter or something like that. And all of the extra data and data files associated with the maps are also available here for download. And you can use those in a software like ArcGIS if you're county staff and working with things like that. There's also something called a story map, which I'm not going to go into today, but it's another resource we have available online to help people look at the data without having to have the fancy expensive software. It's just kind of like a free viewer. But I don't have instruction on that today, but if anybody's interested, you can reach out to the survey and we would be happy to explain how that works to you. So I'm going to go through the plates one by one. I want to stress that I'm a bedrock mapper. I look at rocks. I do not look at sediment. I do not look at glaciers, but I'm going to try to talk about them today. But the first thing up is the database plate. And this is actually a really, really important plate. Every single data point that was analyzed by a geologist for the atlas is on this plate. And they're represented, the different types of data are represented by different symbols. For example, here, a blue open circle is a water well that has a drilling record associated with it. And for example, a red open circle is a gravity point. So that's where we have a geophysical measurement. And you can see on here, anywhere that you zoom into, like, for example, this is called Fish Hook Lake. You can see that there are a lot of private water wells around there, the blue dots, but there are no, very few open red dots. And that just tells you about the density of the data. And you have to remember, I think the most important thing about these atlases is to consider the data density. If you're in a place and looking at an interpretation that somebody made, and you went to the database map and you see all these wells, you say, oh, they probably had a pretty good interpretation because there's lots of data there. But if you want to know what's going on in this part of the county here and you zoom in and there's like one well, that's literally all the information we have. So you have to take it. It's not that we're just randomly guessing what's there, but we just don't have the information to nail it down like we would in a place that has more information. I just threw up here what these well logs look like. This is what geologists work with every day. This kind of gives all the information, locational information about a different well. And then it goes foot by foot and tells you what the drillers encountered as they were drilling it. So 10 feet of gray clay, followed by 5 feet of brown sand, and so forth, so on and so forth. Excuse me. Okay, so now let's talk about plate 2, the bedrock geology. This is my specialty, so I think this is kind of the coolest part of it, but I'm willing to take other opinions. So this is kind of starting at the very, very bottom. The bedrock geology map shows what is at the surface of the bedrock if you took off everything from above it. And that includes all the water, all the trees, all the soil, all of the gravel, all of the sand, and even saprolite, which a lot of people haven't heard of saprolite, but it's just a weathered surface above the bedrock where the rock is kind of grussy and grungy and not quite fully rock. There's a lot of that above the bedrock surface as well. So if you got rid of all of that and moved it somewhere else, this is what the ground beneath your feet would look like in Hubbard County. The plate itself obviously features the map here. Each one of the different colored units represents a different rock type. And that rock type will have a 3-letter code. For example, ABG for Archean, which is the age, Bemidji granite, for example. And you don't really have to know what that is because you have all of this information here to help you figure it out. There's a little bit of explanatory text on the background of the bedrock geology, but each one of these colored units has an explanation of exactly what's in it over here. So you just have to find the corresponding box and code over here, and then you can find out what bedrock is beneath your place of interest. There's also a little chart up here, and these show the box in a time sequence, oldest being down here and youngest being up here, so you can see how the units relate to each other in age. And we'll talk a little bit more about these components in just a second. One of the things that made it really difficult to map the bedrock in Hubbard County is that there are no outcrops, which we all know, and very, very few drill holes go to bedrock. Out of the thousands of drill holes or water wells and scientific drill holes in the state, only 17 actually hit bedrock, and that's it. That's all the samples that we get. So we go, those some of those holes have cores stored up at Hibbing, and we go log it. But other than that, we have to rely on geophysics, and I'll talk about that a little bit in a moment. I'm not going to go into the whole geologic history of Hubbard County right now as much as I would like to, but there are a couple of major takeaways that I want you to have from the bedrock plate. One is that everywhere beneath our feet in Hubbard County at some depth is Precambrian bedrock. Precambrian just means basically really, really old, older than 540 million years old. Everything in Hubbard County actually happens to be Archean, which is The specific rocks here are about 2.7 gigaannum, which means billion years old. So 2,700 million years old. That's the age of most of the rocks you're seeing here in Hubbard County. There are a couple places where younger rocks at 2.1 billion and 1.8 billion years old either overlie or intrude the 2.7 billion year old bedrock. And then locally, you'll see these green patches atop the map. Those are much younger, only 90 million years, as opposed to the billions we've been talking about. Those are Cretaceous rocks that were once laid down over all of Minnesota and have now been mostly eroded, but we find them in local places. So this is what we use when we don't have any outcrop. I mentioned drill core. If you've ever seen a drill rig, you know that they either bring up chips or core when they're drilling beneath the Earth's surface. If the chips come up, this is what they look like. And we kind of sit there at a table and look at them and figure out what minerals are in the chips that come up. What's really cool is when they're able to bring up like full drill core, which we don't get very often, but they take all of that drill core, send it to a repository in Hibbing, and we can go there and log it foot by foot and say, okay, at 450 feet depth beneath the bedrock surface, we know that we have exactly this granite or exactly this gneiss. But in the absence of that, which we had 17 of these in the whole county, we have to use what's called geophysics. I can't pretend to understand the whole math behind the processing of the data, but what I usually do is look at the imagery we have here. We have wonderful magnetic and gravity coverage across the state. And these maps tell me how magnetic and how dense the rock is beneath my feet. For example, a red area means it's really magnetic, and a blue area means it's not magnetic. Similarly, over here, a bright pink or red area means it is really dense, and a blue area means it's not as dense. So what that looks like in Hubbard County is this map here. This is called a smog map, and that means it is superimposed magnetics on gravity. And all that is saying is that in this map, the color scale represents the density. So like bright pink is really dense, blue is not so dense. And you can see beneath the colors that there's like a brightness to it. If it's really bright, like right here, kind of has like that whitish undertone, that is highly magnetic. And if it is not, it's kind of a duller color, that means it's not magnetic. And in the absence of drill holes and outcrops, my job is to go through and look at where the gravity changes. So for example, right here, you have something that's really magnetic and really dense. And you have to think of what rock type that would be. That would be something like a gabbro. You see a lot of those on the North Shore, a really, really dense magnetic rock. And then for example, here, you have something completely non-magnetic and not very dense at all. That's more likely to be something like a sedimentary rock that doesn't have those magnetic minerals in it or really dense crystalline structure. So this whole map was made by interpreting this geophysical data here and also a few drill holes. A couple highlights I just wanted to point out. You have a lot of granitic rocks, felsic rocks, basically kind of pink and black speckled granites like you'd see at a quarry or on a headstone or something. You have a lot of that in the northern part of your county and again in the southern part of your county. These red lines here are something called iron formation. A lot of people don't know it, but the Mesabi and the Vermilion iron formation are not the only iron formations in Minnesota. You have some here in this county. It's just that they're buried by like 1,000 feet of dirt and no one's ever going to mine them. So, but they are there. They're a different age as well. But yeah, just take a look at this and you'll be able to see what kind of rock is beneath your feet. One other thing before, yeah.
Are they Triassic or what age are those?
The iron formations, they're Archean, so about 2.7 billion years old. Yep. The stuff on the Mesabi is quite a bit younger, 1.85 billion years old. So there's kind of like two ages that iron formations exist in Minnesota, but these are the real old ones. Yep. Last, before I leave the bedrock plate, I just wanted to point out that we have cross sections. We do ours a little differently than the quaternary cross sections you'll see in a few minutes, but this is essentially like we're drawing a line from one end of the county to the other, cutting the bedrock in half and looking at it from the side. And the thing that's really important to take away here when you compare it to the younger units we're going to talk about today, a lot of the sediment that's at the Earth's surface was deposited flat. So the layers are going to stack on top of each other. The bedrock in the Precambrian is so old and has undergone so much folding and faulting and mountain building events that none of the layers are flat anymore. They basically dip like 80 to 90 degrees from the surface. So looking at a cross section through the Precambrian rock is very different than looking at a cross section of the much younger stuff that hasn't been deformed and gone through mountain building processes. Okay, enough of the bedrock geology. I wanted to just talk about the bedrock topography. I'm jumping to plate 6 now. I'm not actually sure why they make this plate 6, but the bedrock topography and depth to bedrock is a really important plate for what the DNR uses later on. Bedrock topography means the same thing as surface topography, like how many hills and valleys and where are they, but not on the land surface, on the bedrock surface. And that's really important because that's a very critical hydrologic interface, or it can be. It's not so much in Hubbard because it's buried so deeply, but in a lot of places like on the North Shore where you don't have a ton of sediment, that interface is really critical for water movement. So you have basically an elevation map of the bedrock. And then you have the drift thickness map, or sediment thickness. This is basically made by taking a DEM of the land surface, so like a raster of the land surface, and subtracting the raster of the bedrock surface from it. And then the distance between those two in feet, that's how thick your sediment is. And we'll just get into that in a minute. This just helps you visualize it. This is a little drawing I made. These little sticks here are meant to be water wells. The kind of data we work with, one water well can reach its end and not have even reached bedrock yet. In fact, that's what almost all the wells in this county are like. Sometimes some reach bedrock at higher elevations than others. And it's our job as geologists to take data points. Each one of these down here, these little like data points represent an elevation of bedrock or an elevation of the bottom of a well that didn't hit bedrock. And we hand contour around them, basically playing connect the dots to make an elevation map of the bedrock surface. Some of the highlights here. The highest bedrock in Hubbard County has an elevation of about 1,200 feet above sea level. And that's somewhere right in here. And the lowest is less than 700 feet above sea level. So you have a difference of 500 feet of relief on the bedrock. The highs you can see are kind of clustered right here at the northern border of the county, and in this big high in like central and southern county. And I guess I should say the greens and blues are the low elevations and the reds are the high elevations. But you can see here, there's a nice big valley coming up through the eastern half of the county. It merges with another valley that comes over here from neighboring, I think, Cass County, and it heads out to the North Dakota border from here. And it just gets deeper and deeper the further and further west you go. So that's the drainage surface, not of what's at the surface, right? Because there's all kinds of different rivers there. But this is what, if you were to pour a drop of water on the bedrock surface, that's where it would run. It would kind of head northward and then westward out to the Dakotas. There's no correlation between the land surface topography and the bedrock surface topography because there's so much stuff in between, but there is a bit of correlation with where there are valleys and what type of rocks are there. Generally, when there's softer rocks, you have more erodible rocks and you tend to get valleys in those locations.
Does that have anything to do with flow of glaciers at one time?
It can, yeah. For example, like in the Lake Superior region, you can, like the bedrock surface there is reflective to some extent of glacial carving. Sometimes if there's a high already existing in a place, glaciers will kind of move around it. Yeah, it just sort of depends what age of glaciation you're talking about and how much stuff is already under it. Like the most recent glaciations in Minnesota probably didn't get all the way to the bedrock because there were enough previous iterations, but yeah, good question. And then I just want to talk about the drift thickness. This is what you get when you subtract the elevation of the bedrock surface from the elevation of the land surface anywhere. We call this drift thickness, and drift is basically a derogatory term for glacial sediment, and they don't like when we use that, but it's the drift thickness map. You can see here that it's highly variable across the county, and it looks super intricate. I want you to know that it isn't actually that detailed. This is just what kind of results when you subtract a really detailed 1 meter LiDAR land surface. When you subtract a really general bedrock geology map from it, you get a lot of artificial detail. So it's not that this is that much more intricate than the bedrock surface, it's just calculation made it look that way. Regardless, the thinnest amount of drift or glacial sediment in the county is about 155 feet. And the thickest is possibly nearly 900 feet to bedrock. I say possibly because it's really hard to know with almost no drilling that reaches bedrock. There are a lot of these deep Precambrian valleys that are probably filled with a lot of glacial sediment. They could also be filled with that really young Cretaceous bedrock, and we just can't see it using the geophysical methods that we have. So there could be a lot of that in the valleys too. But basically up to 900 feet of stuff on the bedrock surface in these places where these deep Precambrian valleys underlie high land surface areas. Okay, now we're going to move to plates 3, 4, and 5, which all deal with glacial geology. I'm not a glaciologist, but we have some really, really great glacial experts on staff, and they do a really nice job with these plates. I just want to give a general picture here with this diagram of what a continental ice sheet looks like. I think we all know that at one time, several times in the past several tens of thousands of years, Minnesota was covered with a continental ice sheet. That's what we call a continental glacier, as opposed to an alpine glacier in the Alps or something like that. So it's a large ice sheet, kind of like this. And the ice sheet, of course, is thicker at the poles, and it's thinner down in our latitude. It's not as thick as it would be at the poles. But the ice is constantly advancing as the ice sheet grows. And what it does is it grabs all the sediment underneath it and it piles it up in front of itself. In front of every glacier is what's called a moraine full of till. It's basically a giant like pile at the end of a conveyor belt of sand and gravel and clay and all kinds of stuff. That there's up to 900 feet of that above the bedrock here. And it's not entirely that simple. It's not all till. There are a bunch of different glacial features that make different types of landforms, which we'll talk about. But just think of it as every kind of sediment that you see at the surface across Hubbard County was the result of a glacier moving down from the north and depositing sediment as it goes. Here's the front of an active modern glacier. You can see there's like a river that comes out from the front of it. That's going to leave sediment in the river. So our glacial geologists can see kind of a sinuous shape on the map, and they know that that used to be a river and there should be river sediment in there. There's braided streams, there's outwash, a moraine at the end, all kinds of things. And the glacial geologists read these landforms many tens of thousands of years later to kind of put together a picture of what was happening here in the past. These figures here are just showing past glacial advances. This wasn't just an area that was glaciated once, obviously. These arrows kind of represent the direction ice is coming from, and this green is an ice sheet. You can see that at one point in the past, here's Hubbard County, ice was coming from the northeast to the southwest, bringing all kinds of sediment with it. Eventually, that glacier melted backwards a bit, still bringing sediment forward, and rivers began to kind of break through the till at the end and deposit sediment in little rivers. Later on, this could have been 10,000 years later, a different lobe comes down, also from the northeast, brings more sediment. Then that retreats, and this time a lobe of ice comes in from the left. So you have different lobes of ice through the past several tens of thousands of years, each bringing a bunch of sediment with them. And you can use the landforms to kind of determine what direction they come from, as well as the composition of the sediment there. This diagram is, or this photo montage, I guess, is just here to explain that this is what the stratigraphy of like the glaciology looks like in Hubbard County. There are a number of different formations, all of which are pretty much flat lying, by the way. And each of them, we've squeezed a picture in here of like the front of a glacier, because each one of these types of sediments was deposited by another ice advance. So there have been dozens, I would say, of ice advances over the past several tens to hundreds of thousands of years here. So that brings us to what the plates actually are after our glacial 101. Plate 3 is the superficial geology. This is what's right beneath your feet, but below the soil. We don't actually map the soil, but if you go down a couple feet, this is what is beneath it. Similar to the bedrock map, each colored unit represents a different type of sediment. And you can find all kinds of information about this on the map plate, as well as a whole host of symbols. They use all kinds of arrows and tick marks and shapes to represent the different kinds of sediment. And you can just refer to these as you go looking for wherever your house is, for example, and you want to figure out if it's on clay or on gravel or whatnot. So this is kind of what's right at the surface under the soil. That's plate 3. Plate 4 is one of the most interesting plates for people. This is called quaternary stratigraphy. Remember how I talked about the Precambrian cross sections not being flat lying, all the rocks are kind of tilted on end? This is where you see the opposite of that. Because the glacial sediments are so young, they haven't had a chance to be deformed yet, they're more or less flat lying. So you can see a ton of different layers. Each one of these colors is a different layer, like a different till or a different sand or whatever. They do cross sections at 1 kilometer spacing east to west across the whole county. So there's actually 69 of them in Hubbard. Only these ones in blue here, these 6, are actually published on the plate. But if you download the data, you can get access to all of them. We just highlighted a couple on the plate. And just one thing I want to mention here is that the little black stuff here, those are individual well records. So you can see on line D to D prime, there are a ton of different wells. So there's a lot of different data, and that's helping make a very detailed picture of what's down there. But look at line C. There's like 1 well in the whole western 2/3 of the line, and it's right here. And the rest of this is just inferred from places where there are wells. So that's why the data density is really important. You would be much less confident in an interpretation that was taken right here than you would right here, where there's a lot more data. And the other thing to note is that this white stuff down here is the bedrock. There are so few of these holes that actually go to bedrock that almost everywhere, these bottom few units, we just don't even have samples of. So that's just kind of important to know. Plate 5 is what's called a sand distribution model. It's just a normal map plate like the other map plates, and it shows kind of slices through different sand bodies in the county. It kind of takes and shows a few key slices through it here. But what the real power of this is that you can use these data, which are created by combining those quaternary cross sections that we just talked about with the superficial geology. You can combine those and use modeling software to make an actual surface of a different layer. You can make a surface of a particular till or a particular sand, and it helps you figure out where different units are, how thick they might be, and it gives you like a visual representation of those, which is kind of pretty powerful. And this is something that I believe the DNR uses a lot of ours. They take our sand models and they say, okay, they found a bunch of sand here. That means it could be an aquifer. Now, what is in that aquifer? So I'll just put up 2 maps from the sand model plate. This one is showing all the sand and gravel at the surface and its thickness. The reds and purples are really thick and the blues are not very thick at all. So you can see somewhere here in central Hubbard County, there's up to 100 feet of sand right at the surface. And in other places, there's no sand right at the surface. Another example of what you can see on that plate is called the stacked sands. This tells you at any given location how many sand bodies you could expect to encounter if you drill the hole straight down. And of course, this is all stuff that's generated by modeling. It's not that each of these places we know there's 8 sand bodies, but it's kind of based on the cross sections and the information we do have. This is where it's projected, like you should have a lot of sand right here. And for example, here, I'm not sure what's here, but there's not sand. And I think that that is actually it. So what we do is finish our plates. It takes us about 4 years. And then the whole point of this meeting is because the DNR has finished with their part B. So everything we give them kind of describes the container, the rocks and the sediment that hold the water. And then they get to do the research on the water that's within those. So with that, I will let Nick take it away.
Yeah, so like Crystal said, I'm Nick Buddy. I'm with the Minnesota Department of Natural Resources. We recently, earlier this spring, finished up the Hubbard County Groundwater Atlas app, which builds on the products that the Minnesota Geological Survey had finished a few years before that Amy just presented on. Again, want to acknowledge our funding that comes from the Environmental Natural Resources Trust Fund. That's that lottery money that gets recommended for use by different groups, by Legislative Citizen Commission or Committee. And also we have some funding coming from the Clean Water Land and Legacy Amendment as well. So let's see, there we go. So my talk here today, I'm just going to give a little bit of an overview of where to find Atlas products on our website. Then there's gonna be a little talk about groundwater basics. And then I will go through the major sections of the Hubbard County Groundwater Atlas, which is the hydrogeology, groundwater flow, water chemistry, groundwater pollution sensitivity, hydrogeologic cross sections, and groundwater use. So where to find our groundwater atlas products? So we have physical copies available. For those in the room, if you have not gotten one, they're available by the door to take a look at, and those are yours. You are free to take those with you at the end of the day if you would like to. For those online, or if you wanted to find our products online, you can go to our website. They either go to mndnr.gov/groundwater mapping, or just search for the Minnesota DNR Groundwater Atlas on a search engine. And that should get you to our homepage on the DNR website for the Groundwater Atlas program. And on that page, then there's a little spot where you can go to for groundwater or county atlas. It's down at the bottom of the page or on the side, county CGA. You can click in those places. It'll take you to our county geologic atlas series page where all the county atlases are available for the counties around the state that we have those completed for. So when you're on that page then for the county geologic atlases, there is at the bottom, or when you scroll to a certain point, there's a bunch of letters on the screen. And you can go to navigate to the county, H for Hubbard in this case. It'll jump you to the H's, Hubbard County here. There's a link to the Part A geology on the Minnesota Geological Survey's website. And then there's the downloads for all of the County Atlas Part B products, the report, the 3 plates that we have, and the GIS files, the digital files. So the Hubbard County Groundwater Atlas then, like I just mentioned, consists of a report, which is about 70 pages. It has some major sections that we'll be going over later today in this talk. There's a report here. It's just a nice bound document with pictures. And then we have 3 large kind of large print plates. They're available also as oversized PDFs online. There's one that's going to show the water chemistry locations, and then there are 2 of them that have the cross section or side view, like if you took a slice or dug a trench through the county, what you'd be seeing from the side. And again, also, all these products, as well as our electronic files, are available online on our DNR website as well. So here's our status map then for the Part B Groundwater Atlas. All the counties you see in here that are in the darker blue, those are counties where we have Part B Groundwater Atlases completed. That's 35 counties as of right now. The light blues are the ones we have in progress, and the counties we have not started are in white, with the exception of 2 counties here with the black outline. We actually just started on those earlier this summer, doing some water chemistry sampling in Lake and La Caparra counties in the far northeast and then the west central parts of the state. So just real quickly, how are some of the ways groundwater atlases are used? They can be used for planning and locating water supply wells, whether those be public, private, agricultural wells, the whole variety of uses. They can also be used to help with groundwater resource protection and management, education about groundwater and natural resources, And it can help tell you about pollution sensitivity of groundwater aquifers for use in planning and zoning and community development planning, infrastructure planning as well. And also all the data that we collect, water chemistry data set, all these maps we make, and the digital computer geographic information, GIS files, are available online for local county governments and landowners, homeowners, and the general public to download if they're interested as well. A couple other products that the County Groundwater Atlas group at the DNR works with are our springs, spring shed, and karst data sets. So we have some data sets available on our website that have the Minnesota spring inventory, locations of known springs around the state. We have a groundwater tracing database for any kind of tracing tests that are done on groundwater flow. And we also have karst feature inventory available, which helps identify, which has the locations of different karst features, which have to do with caves and those types of environments in different areas of the state. We also have the hydrogeology atlas for the entire state of Minnesota. So this just basically is a large statewide look at some of the products that we make for such as pollution sensitivity and water table flow and depth to water table type maps that you would also find in the county maps or the county atlases. We have a groundwater provinces map that summarizes the major regions in Minnesota and their groundwater availability. And we also have some of the older regional hydrogeologic assessments, which are really just precursors to the county atlases. They cover larger areas of the state in lesser detail, and they're being replaced by the county atlases as we get those completed. So real quick, a little bit about groundwater basics then. So on this map here, we have a little slice through the earth. We have the surface up here at the top with some nice trees and a stream. And we have water getting into the ground as it rains. It would go down through the surface here, and it would go through an area called the unsaturated zone, where we don't have water at all times. It's not saturated. It's not full of water, I guess, until it reaches a point called the water table. And then below that, then, if it's a sandy area where we have an aquifer, it would be an unconfined aquifer. So this aquifer is not confined to any of finer grained materials. But then if we have a confining bed of finer grained materials, you sometimes also hear these referred to as aquitards. An aquifer below that would be called a confined aquifer. And then you can have maybe another confining bed and another confined aquifer as well. Now we also then can have groundwater flow in these aquifers. And as you'd imagine, these shallow aquifers might take more like days to a few years for groundwater to travel from the surface down into the aquifer and then maybe reach a stream or a water well. Whereas if we get to some of these more confined aquifers that have better protection from clay units above, it might take more like centuries to even thousands of years for groundwater to flow down into the aquifer and then make its way back out through either a well or moving back up, discharging toward the surface at a stream or a lake. And with that, I'm going to move into the Part B report. So the first major section is about the hydrogeology and groundwater flow. It's on the pages 5 through 15 of the report. And just a real quick summary again, and Amy did a good job talking about this earlier, about the geology of Hubbard County. The big takeaways for the groundwater is that we have, hundreds to almost 1,000 feet of glacial sediment, that loose unconsolidated sediment. And there's layers of sand that were deposited as those glaciers advanced and retreated across the county. And those are going to be those aquifers that we're going to be talking about. And they're the major groundwater source for the county. Whereas the bedrock, which is at the base of that overlying sediment, it's not really used much as a groundwater source. So on pages 6 to 7 in the report, then there's a figure about the stratigraphic column. Really what this shows is just all those glacial advances and retreats in the order they occurred, the more recent ones up at the top. And as you move downward, we get to older and older previous glacial advances and retreats and the sediments they deposited. We also on this map, and then it will show the correlation between the coloring you see on the plates for part A, the geologic atlas, and then the coloring we use on some of the figures, especially the hydrogeologic cross sections in our part B atlas. So we can see the correlations between unit names. Sometimes we have names that differ between the two atlases if we lump or split things differently. In this county's case, they're all pretty much the same. It also breaks out the county into, in Hubbard County, we broke the county aquifers into an upper system of aquifers and a lower system of aquifers. So the upper system's going to be aquifers that are either sand bodies at the surface, or they're confined or overlain by really sandy tills. So there's these tills, because they're sandy, allow a lot more interconnection between these aquifers, and they all kind of act as one little bit bigger system, a little bit more flow available between them. As you go into the deeper aquifers, they're less mapped, and they're also more clay-rich sediments, less sandy tills overlying these aquifers. They might be a little bit better confined, and these aquifers are often more isolated from each other and mapped in more isolated pockets, which also partially has to do with the fact that we have limited data from deeper drill holes down there. But we lumped all these together then as a lower system of aquifers, and those ones that fit in each of those categories are highlighted either by the blue bar here for the upper system or the orange bar for the lower system of aquifers. And then lastly on here, we have a quick at a glance look at what figures in the report you'd want to look at for each aquifer if you're looking for the potentiometric surface, so the groundwater flow map, or if you're looking for a pollution sensitivity figure for that specific aquifer associated with a glacial advance and retreat. So the next figure in the report then is just the superficial geology of the county. This is a real generalized look at that. We have the county here basically broken down into, is it a sandy outwash material at the surface, which is given in a kind of lighter tan color, or a more of a till, the little bit more clay-rich materials. That's going to be more of the darker tannish orange color here throughout more of the northern part of the county and central part. And then there's also a darker brown area where we have an old glacial lake basin that over by Akeley that's got some even more clay-rich materials over in that general area. The other thing to see on this map is there's a little overlay here with some speckling in the southern part of the county. So this is just an area that the USGS had delineated back in their 1977 report as the Pineland Sands. We overlaid that on a lot of these maps to kind of just give a rough estimate of where the Pineland Sands delineation is in the respect to the county. And then obviously we're down here in the southwest corner in Park Rapids, where we are at in the room today. The next big parts of the report then are the groundwater or the water table elevation and depth. So again, this is that point where you first hit that area of water saturation in the ground. And the elevation map here shown at the left just shows the level of the water table. It really tracks a lot with the land surface. We'll talk a bit about that with the depth map in a minute. But so where you have higher elevation areas, the groundwater elevation, the water table elevation is also going to be higher. So across the center part of the county here, that east-west line of orange and yellow, that's a higher elevation water table. That's going to be the Itasca Moraine, which is just a higher elevation area across the county. And we have flow then predominantly to the north off of that as part of the Mississippi River watershed, and to the north and east, in the northeast as part of the Leech Lake watershed. And then south of the major divide here across the Itasca Moraine, it's primarily moving more toward the south as part of the Crow Wing River watershed. So the groundwater flow at the water table really is primarily following these surface water boundaries. And the next figure then, figure 6 in the report, is the water table depth map. So this is just a subtraction of the land surface elevation and the water table elevation. So the difference you'd find between those two surfaces. And it is really dependent on where we have data. So if you don't have a lot of well data, surface water elevation data, or soils data that can give us water table elevation information, you might have a little less accurate depth to water table map as well. So bear that in mind. But a lot of the map on here you can kind of see is a very light tan color. That is a less than 10 feet depth to the water table. So this is modeling the water table depth. That's pretty shallow, less than 10 feet through most of the county, but there are some areas where it gets to be a little bit more with the greens and the blues, which are moving up to 50 feet plus. And again, this is really dependent on what data we have available in the location too. So it may not be completely accurate. Then the next major products in the atlas that have to do with groundwater flow are for those buried aquifers, or for those aquifers that are associated with glacial advances and retreats, some of which actually are still found at the surface. And they're lumped into the upper system of sand aquifers, which is shown at the left here, which I told you about. And in this system here, we can see that we have lots of blues and yellows and oranges. Those are the different areas where the aquifer exists. So where there's color, aquifers associated with this upper system of aquifers exist. So it's pretty extensive throughout the county, lots of sands in this upper system throughout the county. Where we have these little black markers, like the pluses and X's, that's everywhere there's a water well that's completed in these aquifers. Again, quite a few of those markers on the map, quite a bit of use coming out of these aquifers. And then we have the groundwater flow directions marked with elevation. So the oranges and the reds are higher elevations, moving to lower elevations in blue. There's also little arrows to help out showing the groundwater flow. And it's really primarily, again, to the north and somewhat to the east off the Itasca Moraine in the center of the county north to the north. And then it's primarily to the south off the center, the Itasca Moraine in the southern part of the county. Now we move to that lower system of aquifers that are buried by more clay-rich sediment. There's a lot less colorful pockets on this map, so a lot less areas that were mapped as aquifers in this deeper system. There's a few pockets up here in the north, a few scattered elsewhere throughout the central part of the county, and then there's a bit more again in the southwest part of the county. A lot less of the black plus and X markers throughout the county as well, which suggests that there are just less wells completed at this depth. Drillers really didn't have to go as deep. They found water where they needed to at shallower depths often. And then the groundwater flow in this system is very broadly a little bit more muted, but it's still pretty much to the northeast off the high elevation Itasca Moraine across the center of the county, and then to the south in the southern part of the county. And then the next part of our report, we talk about water chemistry, and this is really the bread and butter of the rest of the report. We use this to help with a lot of the following products as well. So as a part of our DNR groundwater atlas sampling, we collected water samples from 90 private wells around the county and 10 lake samples in the years 2019 and 2020. And then we also pulled in 60 historical well samples and 4 lake samples from either historical DNR studies that were done in the county or from the Minnesota Department of Health in their databases as well. From some of their samples, maybe they took from some of their community wells. So then we analyzed our DNR chemistry samples for general chemistry. We gave a mineral content analysis to the landowners. So they were sent the results of their test as well. And it includes some, the major mineral content of water: calcium, magnesium, sodium, bicarbonate, nitrate, arsenic, chloride, iron, and the like. We also collected a couple fancier samples than two yet. We collected a parameter called stable isotopes of hydrogen and oxygen, which can help us determine if lake water is recharging groundwater. I'll get into that a little bit more later. And we also collected a couple of resonance time indicators. So we collected one called tritium, which is used to determine if groundwater is getting to your well, through groundwater that is getting to a well recharged before or after the nuclear bomb testing in the 1950s. So if we're seeing this tritium in the water, it means it's pretty recently recharging into the ground. And if we're not seeing it, it's gonna be much older water likely. And then for those older waters that we do not find tritium in, we came back and collected carbon-14 samples, which can give us an estimate if the water is more like 100 years old or is it more like tens of thousands of years old. So to summarize the chloride results then for the county, we found that likely human-introduced chloride, which can come from, among other things, road salt, septic and water softeners, and fertilizers, was likely human-introduced in 34% of wells in the county. And they were primarily from wells less than 100 feet deep in the sandy southern part of the county. So on this plot here, you can see everywhere there's a marker, a little black dot or a yellow or green circle is somewhere where we collected a chloride water sample. Where it's yellow, those are areas where we had that human introduced or anthropogenic chloride concentration. So there's a lot more of them in the sandier southern part of the county here, but there are a few scattered throughout the northern parts of the county as well that are in those yellow dots. Nitrates can be a similar story. The drinking water standard, which is what public water systems are held to, of 10 parts per million was exceeded in 5% of wells. But then we use 1 part per million as a threshold for being above background of what could likely be human introduced nitrate in the groundwater. We found that in 18% of the wells we sampled as part of that are used in the database for this study. Those human sources can be, among other things, fertilizer, septic, and manure. And they were, again, primarily found in wells less than 100 feet deep in the southern part of the county. So the wells where we had the nitrate above 1 part per million are wherever we have the light green dots on the map. So lots of them down here throughout the southern part of the county, and then we see one up here in the northeast as well. Arsenic, on the other hand, is usually a naturally occurring kind of undesirable thing in groundwater. And we found that in 75% of wells in the county. It only exceeded the drinking water standard, however, which is set at 10 parts per billion in 3% of wells. So now that let's talk a little bit about the lake water, groundwater interaction in the county. And to do that, we need to use those stable isotopes of hydrogen and oxygen. So as you probably know, water is H2O, and the H's and the O's, the hydrogens and the oxygens in the water can be slightly heavier sometimes. And if we can measure the amount of that heavier hydrogen and oxygen in it in the water, that actually can tell us a lot about some of the different pathways that the history of the water, I guess, in a way. So on this plot here, we have the amount of heavier hydrogen on the left, the y-axis, the up and down axis here. So the heavier, the more heavier hydrogen, the higher up on the axis you're going. And then same for oxygen, that's on the y-axis on the bottom here. So the more heavier oxygen you have in the water molecule, the further to the right you'll be. Now, most of the time when water falls as rainfall, it's going to plot along this line here, the relationship between the heavier hydrogen and oxygen is going to plot along this line, black line here called the global meteoric water line. So down here in the kind of the bottom left corner of the graph, we see lots of little gray diamonds. Those are water well samples that we determined are likely mostly being sourced by rainwater recharge. However, if your water is sitting in a lake for a long time and you're evaporating, it'll preferentially leave behind some of the heavier versions of the hydrogen and oxygen. And that'll actually shift the line that things plot on off to the right here a little bit. So we took samples from, we have 14 lakes in the county that we were able to plot here and draw a line that represents the water chemistry in these surface water bodies. And we compared the water chemistry of the wells then, these stable isotopes in the well water. And for all the wells that plot along with these lakes here on this red line, the evaporation line that diverges from the rainfall line, all of these wells that plot along here, we can say are likely getting some sort of input from lake water as well to varying degrees. It can be mixed lake water and rainwater, or it can be primarily lake water depending on the well, especially the further you get up here, the more evaporative, the more it diverges off from the meteoric or the rainfall water line. You might be wondering where some of those lake water samples we found, or the samples that indicate potential lake water recharge were found in the county. We found those in 19 of 101 samples that we had this data for in the county. It doesn't mean it's not going to be found in other wells in other areas, but we found it down gradient of several lakes. In particular, we have Hennepin Lake in the north, Lake George here in the central part of the county. I believe that's Wolf Lake up here. And then we moved down to the south. We found it in quite a few areas too yet. Big Sand Lake, Fishhook, Lake Beltane, Spider Lake, Long Lake, and then some of the nothing but the Crow Wing lakes there, I guess. But again, though these wells were often with the lake water evidence of lake water recharge getting into the wells were primarily from wells less than 100 feet deep, and often where we have the sand, which is that light tan color here, is at the surface. So this really highlights that there is a big connection between lake water and groundwater in some areas in this county. Now the residence time indicators, like I said, we have tritium and carbon-14. So tritium, that's going to be, again, if your water is getting into the ground before or after that nuclear bomb testing in the mid 1950s, the peak of that. So if we have tritium in the water, it's going to be referred to as modern tritium age. That's going to be colored in pink throughout the atlas here. If we don't have tritium in the water, it's referred to as pre-modern, or before the modern age. So that's going to be colored with the blue. Now, sometimes we have a little issue with the detection limit now where it's getting to the point where we can't quite tell if it's pre-modern entirely or if it's partially a little bit, maybe a little bit of modern water in there too now. So there's another parameter we had, or another little classification we call mostly pre-modern. So it's still likely mostly pre-modern, that old 1950s water. And that's going to be a lighter blue, and it's going to be lumped together though for most of the discussion in this atlas here. So don't get too hung up on that. I just wanted to bring that up though. And then there's also a green coloring, which is a mixed or mixed description, which is just a mixture between that modern and pre-modern tritium age water. So the tritium age for the samples we collected in the county here that we have data for, we found almost two-thirds of the samples had that modern tritium age water that was recharging since the mid 1950s. So it's pretty young water. Whereas about 16% had that pre-modern or the older tritium age water, and then there was 17% that were mixed. So of that 16% pre-modern, then we were able to collect 8 more carbon-14 samples to get a better estimate of the age of the water. And for those 8 samples, they ranged anywhere from 400 years for the groundwater to get from the surface to the well, or to about 4,500 years. And these are very approximate ages, but it gives you a rough idea of the timeframes we're talking about. I will mention though that we have seen samples that get much older than that. Even in neighboring Wadena County to the south here, we had a couple samples that were over 40,000 years old based on the carbon-14 age dating. So this really just has to do with what wells were selected to sample to yet. We might be just not hitting some of the older water in this county. Then the last plot is a real complicated, fun one in the water chemistry section. This is called the Piper diagram. And it really, what this shows is it shows the major positively charged anion or cations, which are the positively charged constituents in water: magnesium, sodium, potassium, and calcium. On this bottom left triangle, we have those plotting. And if you move to this bottom corner here, it has a higher amount of proportion of calcium. If you move to this top corner here, higher proportion of magnesium. In this corner over here, higher proportion of sodium. So most of our samples are plotting over here in this general area. It tells us that calcium and a little bit of magnesium are the predominant cations in groundwater in the county. We have one notable outlier sitting over here with a higher amount of sodium. This actually is from a 400-foot deep well. It's the deepest well we sampled in the county. That could just be a naturally saltier water in that well down there. And then this triangle on the left is for the negatively charged ions in the county, or atoms in the water. And we have, so that's sulfate, which is the higher proportions of that we plot in the top corner here. Bottom left, higher proportions of bicarbonate. And then the bottom right, we have higher proportions of chloride and nitrate. And again, most of those samples plot in the bottom left corner. Bicarbonate is the dominant anion in the water. And with the exception of, we have a little bit of a drift here along toward the chloride and nitrate. So those samples where we saw those higher concentrations of chloride from anthropogenic or human sources, they're marked with little orange pluses, a little hard to see, but they're there on these ones that are kind of drifting out to the right away from these that are pink and green. So that's just that chloride and nitrate concentrations being a little bit higher, pulling some of those samples away from the majority of the rest of the samples over dominated by bicarbonate. And then we also have this one blue sample here again. That's that old water in that deep 400-foot well that might have some more natural chloride in the water as well. And then we can project from both of these triangles up into the central diamond to get an overall picture of the water chemistry and really see if we have any outliers. Again, that one blue sample is really an outlier here with that different chemistry in that deep well. But if we move to the left corner of this diamond, it just shows that the majority of the samples in the county are dominated by calcium, magnesium, and bicarbonate as the constituents in the groundwater. So lastly, then I'm going to point out that we have the full size plate in the atlases, plate 7, that summarizes the water chemistry for the entire county. So each of those aquifers associated with a glacial advance and retreat is assigned a different symbol on here. And those will be colored pink, blue, or green based on that tritium age of the groundwater. And so you can see where we collected samples, the age, tritium age of the sample. Will also include a carbon-14 age if we collected one for that in a bold black font. It'll have the nitrate concentration if it's greater than 1 part per million and likely anthropogenic in a green font. We'll have chloride on there shown if it's greater than 5 parts per million and anthropogenic, with no marker if it's potentially naturally elevated chloride based on a chloride bromide ratio, which I'm not going to get into right now. That can tell us if it's either anthropogenic human introduced or if it's naturally elevated chloride. That'll be marked on there with I believe that's an asterisk. Yep. And if we can't make a determination on the source, it'll be marked with a little plus sign after the number. We also show arsenic and manganese concentrations on this map to you if they're above certain thresholds. And then if it has that evaporative signature based on those stable isotopes of water. Now, the next big part of the report then is the groundwater pollution sensitivity. This is the bulk of the report, pages 29 through 46. There's 2 major parts of the pollution sensitivity section. We have the near surface pollution sensitivity map, which is for the upper 10 feet of the subsurface, basically that package of materials above where generally the water table is. And it's the estimated speed of that it would take for a pollutant to move with water from that surface down to that 10-foot depth. So to calculate this, we use the top 3 feet from the hydrologic soil group provided by the NRCS's soil mapping in the county. And then the next 7 feet, we pull in the MGS's plate on the surficial geology. And we combine these to get a surficial or a look at the pollution sensitivity of these surficial materials. And the sandier it is, the higher the transmission rate and the higher the sensitivity rating. So an area that would be assigned a high pollution sensitivity rating for the near surface materials might take a week to hours or hours to a week to move through that upper 10 feet. Whereas then you move into moderate, low, very low sensitivity, we're moving toward a year to move through the upper 10 feet. We're getting to be much more fine-grained, clay-rich materials, where it might take years to a decade by the time you get to some of those ultra-low sensitivity areas. So the map for Hubbard County then, you can see on here, we have a lot of red in the southern part of the county and some channels up in the northern part of the county as well. That's that high pollution sensitivity. It could take an hour to weeks to move through that upper 10 feet of the subsurface. And then the areas where we have that lighter tan and light brown, that's going to be a moderate to low pollution sensitivity, or it might take more like a week to months to move through that upper 10 feet of the subsurface. And then there actually is a small pocket over where that glacial lake by Akeley, those real fine-grained materials that have a very low sensitivity for the near surface, where it might take more like a month to year. Then the other major pollution sensitivity maps we have in the atlas is the buried aquifer pollution sensitivity. So there's going to be a whole bunch of figures in the atlas for each of the glacial advances and retreats that are significant uses as aquifers in the county. And these are based on the sand mapping that the MGS did and then the intervening tills. So what we can do is we can calculate how much of that fine-grained till is above a sand body. The more fine-grained material you have, the better protection we can assume it gives. And that would give a lower sensitivity rating if you have more and more material. So if you have a thickness of 0 to 10 feet of that till material above a sand body, it's going to be assigned a very high sensitivity. And it might take more like days to months for water to get to an aquifer with a very high sensitivity. And then high 10 to 20 feet, moderate 20 to 30, low 30 to 40 feet of material. And then if you have greater than 40 feet of till above an aquifer, it would be assigned a very low sensitivity, where it might take centuries or more potentially for groundwater to reach that if it was moving directly vertically downward from the surface into the aquifer, which, as we know, is not always the case. We also have groundwater flow. I'll talk about that in a minute. So here's just a visual representation then of that kind of addition of the till units to make the pollution sensitivity. So if you look over here in this column labeled A, this is a side view again of a hypothetical look at the subsurface. We have the elevation plotting on the left here, and so we have the land surface. We have a sand body in yellow here, or kind of a tan at the surface. And then we have a light gray, fine grained sediment number 1 that's 5 feet thick. So since it's 5 feet thick, it doesn't hit that 10-foot threshold. So we would assign this buried sand right here at this location of very high sensitivity. Now we have another 7 feet of a fine grained till sediment here. Below that, so we have 5 feet plus 7 feet is 12 feet. Now we're above that 10-foot threshold, so it's only assigned a high sensitivity for this next buried sand body as you move deeper. And then if you move down to the bedrock surface in this case, it would be 5 foot plus 7 foot plus 11 feet of undifferentiated sediment. That'd be sediment we don't know what exactly is going on down there. There's not enough well data to tell us, but we're just going to assume it's all fine-grained till materials. You add that up and it would give you a moderate sensitivity in this location. And then just to show you too, yet if you can have sometimes, these till units will vary in thickness. You can have 20 feet of thickness in one area, giving a moderate sensitivity in this aquifer in this spot. But then if you go a little ways away, you might have 40 feet of the fine grained material above an aquifer, giving it a very low sensitivity. So the sensitivity in each individual aquifer pocket can vary across the space too yet. Now, like I said, that's all assuming groundwater moves directly downward. But as I was telling you earlier, we have groundwater flowing laterally too yet. Like I said, kind of north and south off the central parts of the county predominantly. So you can sometimes have groundwater getting in to an area of higher sensitivity and then moving to an area of lower sensitivity, and we'll still maybe get tritium, which indicates younger water, and which would suggest it's more sensitive to pollution at the surface. But it's applying an area that's going to have very low sensitivity, so you wouldn't expect it there. Well, we would assign, if we can see that groundwater flow likely moved it from that higher sensitivity area to the lower sensitivity area, we will assign it a special condition for the lateral flow of groundwater with a little L on the pollution sensitivity maps. Sometimes pumping from city wells, high capacity irrigation wells, other major permitted users of groundwater can also pull groundwater in directions opposite or different than what you would expect, or to deeper depths than you may expect sometimes. In those cases, we would assign a special condition called P for pumping. And then you also may have groundwater discharging. So moving upward, we have older water moving upward and getting into shallower depths than you'd expect. So we might see some really old water at a shallow depth where you might not expect it to be, as it's moving up discharging toward a lake or a stream. In those cases, we'd mark it with a D or a discharge condition. And then lastly, sometimes we just don't know what's going on. So we will give it a U for an unknown condition. And oftentimes that might have to do with just a well construction issue where water could be getting in along the well casing and more quickly getting down to the bottom of the well where the screen and pump are, than you would expect if it was moving through the sediments, further away from the well. Or sometimes you just really have no idea what's going on. So here's a couple of examples of those pollution sensitivity maps. Then I picked a shallowly buried one, so one that's not far below the surface. And then that's gonna be figure 21 in the report. And then we also picked, I will be showing you in a minute here, one that's a little bit more deeply buried to compare and contrast what you might find on some of these maps. So on here, you'll see a lot of red in the southern part of the county. That's that very high sensitivity where not a lot of fine-grained materials protecting this aquifer in this part of the county. And there's some red scattered elsewhere throughout the northern and central parts of the county too yet. We also see there's little bits in green and the in-between colors of oranges and yellows too yet for those moderate sensitivities too. And then we will use the groundwater chemistry, so the tritium age dating. If it's recently recharging into the ground, that would suggest it's got a higher sensitivity. It's going to be quicker travel times. It's been recharging since the 1950s or so. Or if it doesn't have that, it's suggesting older groundwater. So we'll use that to verify the model. We'll also use if there's nitrate being found in the water at higher concentrations, or if we're finding those higher concentrations of human introduced chloride in the water. And you'll see on this map, we do have a lot of the pink diamonds here for this aquifer, showing that we found a lot of the younger water in these aquifers, supporting the higher sensitivities at this shallowly buried aquifer system. Now, as we move to a little bit deeper one here, you'll see the aquifers again, a little less. There's just a little less of this aquifer, all the areas where we have colors where this aquifer unit exists. There's a lot more green on this map. A few pockets up here in the north, a lot more green pockets down here in the south. Then there are some higher sensitivity areas over here with the yellows and even moving into the red for very high sensitivity. But a lot of it's that green, very low sensitivity, where we're estimating maybe 100 years or more for groundwater to get into the aquifer in those areas. And then again, we're using groundwater chemistry to help verify these sensitivity ratings. And in some parts of the county, like in particularly down in the southwestern part here, we have a lot of L's and P's, so we can have groundwater through just its natural movement or from pumping, potentially pulling it into areas of lower sensitivity than you would expect to be finding this young water. So we have some of those pink younger water samples that we collected down in this part of the county here in this unit, given those special conditions I just talked about, the P's and the L's. Then we also do have a few of the blue, mostly pre-modern or the old pre-1950s water that confirms the low sensitivity of other areas. So there's one down here, and we have one up here in the blue. And the sample down here also has a carbon-14 age date of 3,000 years, which is definitely supporting that it's going to be greater than a 100-year or a century travel time to the aquifer in that area. The next part then is the hydrogeologic cross sections. So there's a little description of each of these in the report on pages 47 to 49 to go along with those big plates that we have in plates 8 and 9 for this county. That are those slices through the county. Like if you were looking at it from a side through like from a hypothetical trench that you dug through the county. So just to real quick kind of pull that figure I showed you earlier about the pollution sensitivity and to pull those special conditions into cross-section view for you to look at. We have the pumping here, pulling this green color mixed tritium age, the younger water down into a deeper area where it's mostly finding blue water down here. We also can see an area here where we have that lower amount of protection in this part of this aquifer overlying this green aquifer here, where we over here we saw a little bit more protection. So we would expect it to be potentially older water, but we have the groundwater moving as these arrows show toward the right in this figure. So that could be moving groundwater laterally into these areas of lower sensitivity. And then also, as I mentioned, we can see that upward movement, sometimes of groundwater discharging toward lakes or streams as well. So I'm going to show you an example of an east-west slice through Hubbard County here then. And so this is just one of the pollution sensitivity maps for the HSA unit, which was deposited by a specific glacial advance and retreat. We have these lines cutting across the figures that have letters at the end. In this case, it's F and F prime, that the prime would be that little X or apostrophe after it. And so if you wanted to look at what the slice F prime looks like, you can go to plate number 9 and look at the cross section labeled F. And this is what you would see. I'm going to zoom in a little bit more on this far eastern end of this cross section boxed in by green here and give you a little bit of a walkthrough of what you're seeing on this cross section then. So plotting along the edges of these, we have the land elevation again. So the land surface, which would be at about 1,400 feet to 1,500 feet, depending on where you are in this cross section. And then it's also vertically exaggerated 50 times. So you're seeing about 50 times more of a stretching in the vertical direction than you would horizontally, which just gives us it makes us able to more easily see the units as we look at it from the side here. But it also does give the county a bit more of a sawtooth type appearance at the surface, it isn't really that sawtoothed. That's just a result of the vertical exaggeration. And then on these cross sections, we have the till units, or which are usually going to be aquatards, colored in as light, different shades of light to dark gray, depending on their sand content. So the sandier units, like I mentioned, closer to the surface, those tills are a little bit sandier. They're going to be plotting as a lighter gray color. You'll see those up here and near the surface. And then as you move a little deeper, they get a little less sandy, a little bit more clay and silt rich. Those ones are going to be a darker gray color. And then we have the bedrock down here plotted in kind of a dark-ish, tealish color here. And then the sediment where we don't have the mapping information available is colored in brown. Now the aquifers, then, those are the sand bodies where we're pulling water from. Those are going to be colored based on the tritium age of the water. So the pink for that post-1950s modern water, green for mixed, and blue for the pre-modern or pre-1950s water. And then each aquifer also has kind of a little hatching pattern or speckling or vertical bars to delineate which unit it is, in case we can't always fit a label in there. And those, for reference, will be printed on the side. The patterns will be printed along the side in the legend, and they're also in the stratigraphic column earlier in the report for your reference to it. But most of the time when we can try to fit a label on there of the unit name, we will try to do that. And then also these vertical sticks on here, again, those are all the well sticks. For wells that we have samples from, the little well screen box down here will have a color shading in it. So in this case right here, there's a blue shading. So we got a sample from this well that came back with the pre-modern tritium age water. But if it's gray, it means we did not collect a water sample from that well, but it's still showing roughly where the well screen is for these wells. You'll also notice again, as I mentioned earlier with the groundwater flow map, a lot more wells up in the shallower upper system of aquifers, a lot more of those vertical sticks. And there's just a lot more of those aquifers mapped than there are the deeper aquifers. On these cross sections, you'll also see some other symbology, including the markers again for chloride and nitrate concentrations. We also have the carbon-14 age dates, which we actually have for the sample down here that I mentioned in pre-modern tritium age water. We came back and got a sample that showed that this water in this well took about 1,400 years to get from the surface down into this 300-foot deep well. We also will show on these maps areas where we have that evaporative signature. So lake water potentially getting into wells. We see several wells over here near Spider Lake in this area getting that E. So we have lake water definitely getting down into the ground and contributing to the groundwater recharge in this vicinity. And then lastly, we kind of have a very cartoonized depiction of groundwater flow given with groundwater elevation lines, which are these dotted lines here with elevations labeled on them, and then flow arrows showing groundwater flow direction, which in this particular location is really dominantly downward and a little bit to the east. And then lastly, there are those special conditions that we talked about where you might find tritium in areas you don't expect it to be. Those are again marked on these cross sections as well. So in this area over here, we have a few P's and a U flagged. So right over here, we have a couple of aquifers that are buried under some of these darker gray tills. There's a lot of protection for them. You wouldn't really expect to find younger water in there, recently recharged water in these aquifers. But if you look at the permitting database for where the high capacity permitted wells are, there are a few high capacity wells in the general areas in these same sand bodies just within a couple miles that could be pulling the water down a little bit deeper into these units in areas where it might not be as much protection. And then there's also a U here marking this sample here where we have a green, which is showing that mixed stage. You wouldn't really expect to see a mixed above younger water, the pink. Usually it's going to go pink, then green, then blue as you move downward. So we're not really sure what's going on right here. It could be a case of the pumping, that's pulling water in down into these aquifers below, isn't really pulling it over into this area. So there's just an isolated pocket of slightly older water right here. But that's really just the best guess at this point for what we can do in this situation, which is why we assign an unknown condition to some things like that. Then the last major section in the report is the aquifer characteristics and groundwater use section. So that talks about there's a real small summary of well and aquifer tests that we have data for in the DNR database for the county. We test specific capacity, which is the amount the well water draws down compared to the pumping rates. The more you can pump it with the less drawdown, the higher specific capacity the well has. We have data for those for tests, which are often short-term and upon well completion for larger diameter wells. I think we used 6-inch or greater. For everywhere there's a gray marker on the map here. So a lot more of those again are available down in the southern part of the county. The Pineland sands are in that general area. And then also wherever there's an aquifer test that there's data available for, which is just a measure of to get a measure of the aquifer's capacity to transmit water, done with a longer term, larger scale test. Those are marked with the red markers on this map. And there are, I think, somewhere around 5 to 10 of those. And then there's a table following that in the report that summarizes the breakdown of these aquifer tests for transmissivity and the specific capacity values, giving mean values, minimum and maximums for each of the upper system of aquifer glacial advance and retreat units, and then the lower system of aquifer sand bodies from the different glacial advances as well. And then there's also a little bit of an overview of the DNR observation wells that are available in the county. So the DNR maintains an observation well network that stores water levels from these in a publicly available database. And on this map here, we just marked where all the different currently being monitored observation wells are in the county by the DNR. And they're coded either blue if they're part of that upper system of aquifers that are more interconnected through the sands, or orange if they're part of that deeper lower system of aquifers. And then if the depth or aquifer system is unknown, it may be marked with a gray star instead. Then I also want to highlight in the southwest over here, kind of just south of Park Rapids, there are 2 well nests that we pulled hydrographs in for of the water levels in the wells. I'll be talking about those in the next couple of slides, one of which is just north of the Straight River, southwest of town in Park Rapids here. And then the other one is right where Highway 71 is crossing over the Straight River south of town. So the first one, this is the one that's about a mile north of the Straight River. This is just showing water levels. The higher the water level in the well, the higher it is on the Y or the up and down axis. And then this is, as we move, is showing 4 years of time from 2016 through 2019 on the Y axis. We have rainfall plotting on the bottom here. That the amount of rainfall monthly is marked on this. The y-axis here, an irrigation well. So what you're seeing here is just the irrigation well cycling on and off during the irrigation well, where water levels will drop and then recover, drop and recover. So this well that's plotting in orange is 145 feet deep. And then, like I said, it's right within the vicinity of a irrigation well. And this blue line is for a 34-foot deep well, a much shallower well. That is right, it's right in this next to the other well. So they're a nest, one's shallower, one's deeper. And we're not seeing the pumping signature in the shallower well here, showing that there's a bit of isolation between the shallower system and the deeper system at this location. And then we're seeing that we're seeing the pumping in the deeper aquifer recovering up and kind of tracking with water levels in the shallower system as well, which are more dominated by precipitation patterns. Now, the second hydrographs for near Highway 71, there are 3 wells at this location, and then there's also a stream gauge that the USGS has on the Straight River. And in this case, the shallowest well actually is plotting at the lowest level here. So there's a 12-foot deep well plotting with I think it's the purple line is that well. And then there's a 26-foot deep well, which is the light blue line here. And then a 75-foot deep well, which is the orange line. And then the Straight River, like I said, is in yellow. So that tracks pretty closely with the shallowest groundwater well at that location. And then we have a So groundwater will want to move from higher elevation to lower elevation, right? So in this case, though, we have a higher groundwater elevation in the shallower or the deeper wells than the shallower wells. So what this is really showing is we have an upwelling of groundwater at this location from the ground into the straight river. And then we also do see a little bit of pumping effects in some parts of the year on this deeper aquifer well, which can sometimes be pulling the groundwater levels down below that of the moderate depth well and reversing the gradient once in a while during this 4-year time frame, again, of 2016 to 2019. I will also want to point out that if you do want more information about the groundwater levels in the Straight River area, the DNR has several reports out on that area, and I would encourage you to look at those if you have any more questions and reach out to other DNR staff, local DNR staff, such as Darren Hoverson, for more information. And then lastly, the permitted groundwater use is summarized for the county in 2 figures, figures 35 and 36. So DNR permits are required if you pull more than 10,000 gallons per day or 1 million gallons per year. And on this map here, it'll just show it by use type. So green dots are for agricultural irrigation permitted use. Blue dots, we have a couple of those here. Those are municipal use wells, city wells, and yellows for agricultural, it's agricultural and food processing. So those are the 3 major users in the county here. Lots of irrigation to it, as you all well know. That's the dominant color on this map. And then there's also a table that summarizes the groundwater use in the county, again, broken out by the aquifer, the upper system, the lower system of aquifers, and then by the different use types. And then at the bottom, we also compare the use, since this is a snapshot in time that we used in this report for the year 2020 in this case, it compares that to the previous years from 2016 to 2020 to just show, is this a high water use year or a low water use year, and how it compares to the surrounding years that we have data available for. So in this case, we have a lot of numbers near the high for 2016 to 2020, showing that that was a little bit higher water use year. So real quick again, to summarize then, we have the superficial and buried sand aquifers are the major water sources in the county. The tills closer to the surface are much more sand rich, and they provide less protection to the aquifers than the deeper ones that are a little bit more silt and clay rich. We found human introduced chloride and nitrate, primarily in shallower wells in the sandy southern part of the county. We also found some evidence throughout the county of groundwater surface water interaction. And then the vertically stacked and extensive sands in the southern part of the county result in higher groundwater pollution sensitivities at greater depths. And then these also are seeing much greater amounts of use. And then, as I mentioned, much more isolation for aquifers elsewhere in the county. And then agricultural irrigation is the major permitted user of groundwater in the county, again, primarily in the pineland sands and the sandier areas of the south. So with that, I will take any questions you have right now. Otherwise, we will take a small break. Any questions? Anything online, Susan? Okay, we have a question.
Can you explain again about the signature you get from a lake? It's evaporation signature that lets you know where the water's coming.
Yeah. Yep.
Or flowing to.
Sure. Yeah. So the question was to just talk a little bit more about the groundwater evaporation signatures we can see in groundwater and how that can tell us, or how we get that and how that tells us about what that can tell us about groundwater interaction with lakes. So I'm just going to go back to that slide. Let's see once too far. So again, the big part of the story here is that when you have the hydrogen and the oxygen in a water molecule, you can sometimes have heavier versions of those hydrogens and oxygens in the molecule. And most of the time they plot along a line. If they're originating from rainfall, they kind of have a pattern they follow. Whereas if it's sitting in a lake and some of the water evaporates, the lighter ones are more likely to want to evaporate, and it leaves behind a little bit more of the heavier ones. And those ones will cause that, and that kind of mechanism will allow us to see a little bit of a shift in from what you'd expect from rainfall. So if it was rainfall primarily contributing, it would plot along this relationship here, the black line. But with that shift that we see from evaporation, it causes water samples from both lakes and wells to shift off of the line from what we'd expect rainwater to do, and into a more of an evaporative signature here. So we can compare well water sample to the lake water samples that we collected in the county and look for ones that are kind of seeing this little bit of a shift in the relationship. And the wells that we see that follow that kind of shift are ones that would likely be seeing that lake water influence.
So that's how the groundwater is recharged, correct?
Yep.
So typically in that lower end down there, the groundwater is recharging by rainfall predominantly.
Yep, correct. Yes, the lower left is
If you
primarily
move further
rainfall.
On the red line to the right, the water's been sitting in the lake a while. And then percolating down
yep.
into the groundwater.
Yep, and then, so yeah, along the red for those online, yep, that is the area where it's been sitting in a lake and then percolated down and mixed with maybe mixed with other rainfall fed water and made its way into the water wells eventually. Yep. The atlas. Now I will follow with a couple of case study exercises with part B on the atlas as well.
Hi again. So as Nick just said, I'm gonna do a landform exercise. This was put together by a couple of people at the Minnesota Geological Survey, some of our glacial mappers. And this will just help familiarize you with the different symbols and types of landforms on the superficial geology map, which is one of the ones that folks end up using the most from the Part A atlas. So, this is a landform exercise, as I've said. When glaciers move towards one direction, they carry sediment with them and they deposit it in a variety of ways. And that's due to the movement of the ice and the melt water that comes off from beneath the ice and in the front of the ice. There's a couple different landforms that you can see right here. Imagine that this ice sheet was once this far forward. If the ice sheet sat there for a while, the ice continues to actually move forward. The ice itself never moves backwards. It's just that when a glacier recedes, the glacier itself moves, like the extent of it moves backwards, but it's always moving forward like a conveyor belt, always dumping stuff off the front of it. So if this was as far as the ice sheet got at one time, it deposited right here what's called a terminal moraine, which is just kind of like a pile of in a line in front of the largest or the furthest ice extent. And this is kind of composed of clay and boulders and cobbles and all sorts of different sizes of things. Little temporary moraines that can kind of build up if a glacier sort of stalls out as it's retreating. That's a recessional moraine. You can get cames, which are little piles they're almost like circular piles. I think they're composed of a lot of sand, and those can form when there is, I believe, a hole in the ice and sediment can kind of pile in it and drop down. You can also get something called an esker. A subglacial river will be carrying sediment, and eventually it will drop off and drop out enough sediment that when the glacier retreats, even though the subglacial river is gone, the sediment that was there still remains. So you get this long sinuous ridge. You also have features called drumlins. These are streamlined sediment kind of hills that record the direction that ice was moving. So you can tell the direction of elongation is the direction that the ice was moving at that time. And there are a number of other landforms. So looking at Hubbard County, based on the aerial photography here, Hubbard is pretty flat, as we know. It's hard to define glacial landforms, but some of the things that you can see: lakes, forest, roads, farm fields, obviously. But when you get rid of all that vegetation, this is the LIDAR that someone asked about earlier. The state of Minnesota has 1 meter resolution LIDAR, which is just an elevation map across the state. And this strips all the vegetation off and shows you what is actually at the surface. this allows folks to see a lot better the glacial features here. I'm, like I said, not a glacial geologist, and even I can see little river or stream valleys here and like moraines for when sediment was dumped at the front of an ice sheet. You can see rough textures, smooth textures, stream channels, all those kinds of things.
You think that's a recessional moraine?
I don't know enough. I kind of think it's a terminal moraine just based on those diagrams that we were looking at earlier. Is it, Nick?
Yes, it is, yeah.
Okay. Yeah, that's the furthest extent it ever got to. Yeah. So that sounds like, from what Nick's saying, that's what that is, but
Where's that on the map?
right here. So like the ice would have been coming from this direction and dumping stuff continually at the front of it. Yeah. And of course, some stream channels here, things like that. Adding color emphasizes the landforms even more. This is that moraine that we were just talking about. It's got some of the highest elevations too, because it's just like a ridge kind of pushed up, not pushed up, but deposited higher than most of the land around it, which was sort of like flattened by the glacier. These are the map symbols that I was pointing out from the surficial map before. These indicate various different kinds of moraines or troughs or ridges or valleys. And you can check these all out because there's some really good descriptions here. But we're going to go over 4 particular ones and see if we can match them. So these are the different glacial landforms that we're talking about here. And we're going to start with this top left one. And does anyone have a guess which one of these symbols correlates with that? The symbols are for drumlins, which are kind of those streamlined hills that can form under glaciers. Moraine, which is what we just talked about, the kind of pile of till that's deposited at the front of the glacier. A trough or a tunnel valley, so a tunnel running under the ice, or an esker, which is a sinuous glacial stream deposit. Anyone have a guess as to what this one is? Trough tunnel valley. You are right. And that is located, I'm not familiar enough with the surface of Hubbard County to tell exactly where this is, but they're apparently saying that there was a big trough right here and that a bunch of sediment and water could have gone through it.
I don't think so. No.
Lake of the Valley, it says it.
Oh, Lake of the Valley. Okay, next one. What do we think this is? Yep, this is an esker. Even I can tell that one. If you zoom in here, they occur in the northwestern corner of the county. They don't have very high relief in this area and aren't easy to see, but you can sort of see the trace of one right here on LiDAR. It's kind of bumpy, sinuous ridge. I guess that's where you often find gravel pits because they're made of sand and gravel. Next one, this would be, yeah, this is a moraine. It's got what's called hummocky topography, which means it's got a bunch of ups and downs over a short area, and it's a ridge. So this apparently is the edge of a moraine here. I can't tell what part of the county that's from, but then out in front of it, you have in front of a moraine, you usually have like a sort of flat-ish area called an outwash plain, and that's where all the sediment starts dropping off as water comes off the front of the glacier. And apparently, if you're standing on this gravel road here, you can see this elevated area is a moraine. It doesn't have a ton of relief here, like in some counties, but that's apparently because so much sand was deposited in front of it that it doesn't have that same high relief anymore. So then that leaves us with this final one, which is then a drumlin. These are, each of these arrows kind of points out a drumlin, and the arrow obviously points in the direction that the ice was flowing. These are those streamlined hills that form associated with glacial ice movement. And apparently if you're standing on this county road right here, you can look at a drumlin crossing the road, and it's got a rise of about 45 feet. And these are found, I can't move the, here we go. These are found in the southeastern corner of Becker County, where they are much more subdued and harder to see than you might, than something like this, which is a picture apparently from Ireland. So that's it for us. This is one of our Giddings trucks. This is how the glacial geologists determine what's kind of beneath the surface sediment. They take a truck mounted auger and go down, 15 to 20 feet to kind of bring up sediment samples and analyze them. So that's it for the glacial exercise.
Okay, thanks, Amy. And I'm going to do a quick slide change here to get to the part B exercises. So bear with me for a moment. Let's try this. Okay, Susan, are you seeing my slides correctly in the online?
Yeah.
Okay, perfect. So I'm going to go through a couple of quick case study exercises now on how you might use the Part B groundwater atlas. So the first of these is going to be just an emergency spill response case study. So say you have a tanker truck spill, unknown liquids are released, and area emergency responders are asking, what are some potential groundwater impacts that might be coming from this spill? So we know location is along Highway 71, just hypothetically in this case, so just south of the Beltrami County line, so in the northern part of the county. So it's up in this general area up here. This is about a 4 miles diameter circle, just for reference to yet. So what information can you quickly gather from the groundwater atlas? So what are some of the major things we could learn from an atlas if people want to shout those out or maybe put things in the chat?
Pollution sensitivity.
Yep.
Flow of the material.
Yep, pollution sensitivity, flow. Yep, those are a few of the things. So I'm going to start stepping through a few of those then, and we're going to see what we can learn from the atlas about those different aspects. So one of the big ones that you might not think of is just looking at the original overall county map, which has the watersheds listed on it and the surface water watersheds, and you can get a rough idea of what impacted surface water features might, or what surface water features might even be impacted. So based on this, a spill in this green circled area on the map, what are some potential nearby water bodies that we could be impacting? Yep. So yeah, we have actually, it's an interesting spot, which is kind of why I picked this location. We're right on a watershed divide, which is this pink line. So we could have water flowing toward the west, toward the lake here. We also could have potentially, if you're in certain spots, it could be flowing toward the east here too, toward some of these Necktie River and tributaries as well. So then we can move into the superficial geology figure and get a brief look at what the overall general superficial geology for the area might be. So on this map here, we have till in the tan, and remember outwashes are the lighter colored tan, and the darker colored tan would be till. What's the superficial geology in the area? It's going to be the darker tan, which is mostly till at the surface in the area here. Then you can move into the groundwater flow maps. So groundwater flow at the water table. In the circle here, we have the higher elevations. Again, with the lighter blues moving to darker blues at lower elevations. So what directions are water going to be flowing in this location from a spill that would happen along the highway? Yep. So it'd be, west or east, likely to the west, because most of the highway is mostly to the west of the watershed divide. But there could be some groundwater flow at the water table again toward the east as well. Now the depth to the water table on this figure here, again, the lightest tan is a 0 to 10 foot depth to the water table. And as you move up through the darker colors, you get to greater than 50 feet in the dark blue. What's the predominant color in the circle here? Yep, 0 to 10, correct. Thank you. And there's a few pockets again of the greater depth in that area too yet, but it's mostly less than 10 feet. The shallower aquifers, so that upper aquifer system, then what can this map tell us? A, about groundwater flow, and B, is there a lot of wells in the area? So remember, the wells are the black markers. Everywhere there's a colored shading on the map here is an area where the aquifer is present, and then we have kind of rough arrows showing groundwater flow direction. So I guess the big stories here, again, it's that west or east off that groundwater flow divide from the highway. We have an extensive amount of these upper system aquifers, lots of color, kind of blue shading on the map. And there's quite a few wells that could potentially intercept contaminants if it were to get to them, because there's a lot of those black plus and X markers on this figure. Now, if we move to that deeper, lower system of aquifers, what's different about this map? It's going to be, again, west or east potentially for groundwater flow. But there's fewer aquifers down here and fewer wells. And what we really want to do for these areas is check pollution sensitivity. Are these going to be very sensitive to a spill at the surface? Is it going to, if it's going to take hundreds of years, are these deeper wells even something we're going to have to worry about? So we'll step in then to the pollution sensitivity. So this is that near surface pollution sensitivity figure. It's the upper 10 feet of the subsurface again. And we have the higher sensitivities are red, moderates and lows are the light tans, and then very low is a darker brown. What kind of sensitivity are we seeing primarily in the area here circled? Yep, low to moderate, correct. So that's going to suggest, it might take weeks to months for a travel time just to get to a depth of 10 feet where the water table would approximately be at. Question?
I was thinking back to one of the earlier slides where there was a whole bunch of wells and it was 0 to 10 feet to them. So why wouldn't they be at risk of pollution?
So this is the this is just that area getting down to the water table. Actually, the next slide here is once we actually get into an aquifer, a buried aquifer, the risk they have. And we saw a lot of wells in these shallower aquifers on a previous slide. So, and that leads me to ask on this figure here, this is for so if you start stepping downward through all those different aquifer units, this is the one that's the shallowest up near the surface. We have a lot of, what sensitivities are we seeing a lot of on this map here? The reds are the very high sensitivity, orange is high, yellow is moderate, green is low and very low. Yep, correct. So we're seeing a lot of, very high to moderate sensitivities in the area. So, there is a potential to reach these uppermost aquifer in some of those wells in hours to months. So then we can continue checking some deeper aquifers. So if we move down to the next one below that, this is the second aquifer that's got a pollution sensitivity figure for it. It's just below the one that we just looked at. There's a little more protection in some areas than this one. So we're seeing a little more green on this map. So it's mostly very low sensitivity, but we still have some of those pockets up to very high sensitivity here as well. Some of the reds are again. And we actually have a well sample in this area too yet from this aquifer. So that's what this little marker, diamond marker is. So we can see that we have evidence of that younger water, that it's taken at most 70 years for water to get into this well from the surface based on the fact that it had that modern tritium age water. We're also seeing a chloride concentration that suggests that an elevated chloride concentration suggesting possible human impacts as well. So it's showing this aquifer could be impacted by activities at the surface, even though in this case, it's plotting this well sample, plots in an area of very low sensitivity. Since we have those areas of up to very high sensitivity in the area, which showing that groundwater can still when it flows, move it into these areas of, it can move this younger, more, more at-risk water, I guess, into the areas of lower sensitivity in this aquifer. So then you can keep stepping down through the figures 22, 23, keep going, doing a similar type thing, looking at how the sensitivity changes with depth. It's going to get, as you'd expect, probably less and less sensitive. And you can see if they're even present in the area. If there's no coloring on the map in the area, the aquifer is not even present, and you don't need to look at that one. But then as we keep going deeper, we get to the BRS2C aquifer in this case, which is shown on figure 24 in the report. So this is the first aquifer that's part of that lower system of aquifers that actually has that more competently confining units, the less sand rich, the more clay and silt rich till over it. And what sensitivity are we seeing a lot in this unit then? Again, green's very low, correct. So this aquifer here then is going to have a very low sensitivity, as do all deeper aquifers. So if for very low sensitivities, we're talking orders of hundreds of years potentially for groundwater to get there. They're likely not as at risk to a spill up at the surface. So another thing we can look at then is, are there nearby cross sections in the report? So on those pollution sensitivity figures, like I mentioned, you have those west-east slice lines across on there. And look at this, we have one actually going right through the general area. It's line A. So we can go look then at plate 8 and look at cross section A prime on that plate, and look at the text on page 47 in the report to get a bit of a narrative about it. And we can get a lot of the same information actually again off this cross section. So here's the highway up in this high elevation area. And we have the groundwater flowing both to the west, toward the lake, and toward the east, offing up there. We can again see all those shallowly buried aquifers. So we have all these pink shaded kind of with the dashed lines. Those are aquifers that are shallowly buried by gray shaded till units here, with little bits of till intervening in between here with the light gray shades as well. So it's again also showing that younger water pink shading in these interconnected aquifers. So we had that one sample earlier we saw, that's right here, that had that young post 1950s water. So we can see that pink shaded well right here again, with that also showing that that chloride concentration that we've identified in the well, that the higher chloride concentration. And how that, we can see that there is quite a bit of interconnectedness between these aquifers, lots of sand, lots of potential for rapid transit of water that moves a lot faster through the sands than it would through some of these more clay-rich till units. As I mentioned, you see the sandy till near the surface, and you can also see that a lot of the wells, like we saw in an earlier figure, are found at the shallower depths that might be more at risk here. That there's not a ton of deeper wells in this area. Now, the last thing you can do is there much nearby for permanent water use in the circle? Are we seeing anything there? Nope, there's nothing really in the circle, but there is a one pink dot nearby. So there's a golf course irrigation source nearby. So if there were more things in the circle, those might be big users that you might want to let know if there's a spill, if the spill might impact their water quality and their uses for it. And then you can also check so this is one thing you can do by use type on figure 35. And if you go to the next figure in the back of the report there to figure 36, you can see which aquifer system that user is in, if it's in the shallower system, upper system, or if it's in the deeper system. And in this case, that golf course irrigation one would be in the shallower upper system. Okay, and then I'm going to move on to the second case study here. This one's just about a well location. So let's say you want to learn more about the pollution sensitivity and chemistry near your well. So I'm going to use an example that for a well that the address is near Dorset. And what can you learn from the atlas and other resources about the well here? So one thing I'd like to point out to people that they may not know always is you can often get access to the driller logs that Amy mentioned earlier that the MGS bases a lot of their geologic mapping on. You can get access to those online. if your well was drilled since the mid 1970s, you can likely find a driller's log. It's still, they don't always all get submitted, but so they might not be there, but there's a decent chance if your well's newer, especially in the last couple decades, that there will be a record in there for your well. So if you just search for the Minnesota Well Index on your browser, it'll come up to you can get to a map viewer that looks something like this. And you can enter an address into the search bar. It'll zoom into your address then. You can turn on a base map here for the aerial imagery if that helps you locate your well as well too yet. So I just typed in here, it's an address for the Henrietta Township Hall over near Dorset as an example. And we found a well, and it has the well name, which is the person who drilled the well, and it was the township that drilled it. So oh, yep, we have the right well here. It tells you also the depth of the well, and then there's an aquifer code here. This doesn't necessarily match what's in the Part B atlas. This is just a sign to tell you if it's in the quaternary sediment, so the glacial sediment, or if it's in a bedrock type well. So that's what this code will tell you here. And then in this case, like I said, the well depth is 95 feet. So once you click on you can click on here for see more information, and it'll bring you to another page where you can click see driller's log option, which will bring up the log here. You can usually see the scanned version that's just handwritten in or typewritten or digitally entered by the well driller, depending on when it was done. And then you can get to the one that's digitized here, a little bit easier to read sometimes. And this has a whole plethora of information available about the well. So it'll have what the driller encountered on their way down drilling through. So in this well's case, gravel, sand. So they were hitting sand and gravel the whole way down on this well to 95-foot depth. It also tells you what diameter the well casing is and how deep they went with that, and where the screen is located, so where the actual opening to the aquifer is. So in this case, the well is open to the aquifer from 91 feet to 95 feet depth. It also tells what the water level in the well was at the time they installed it. So in this case, it was 50 feet down from the land surface to get to the water level in the well. And there's some information about pumping, about how much they could pump, and the amount of water level drawdown over a certain period of time, pumping at a certain rate. There's information about your well head completion and your pump. You can see where your pump is set. In this case, it's 85 feet or 80 feet down in the well, so 15 feet off the bottom. And there's a few other pieces of information too, like some near sources of contamination that the drillers were able to identify. So like easily like septic tanks, those types of things. And then the driller's name also is usually found on these in the bottom. So the tricky part then is, okay, you know your well, you know the well depth. What aquifer are you in? This is where it can get a little tricky sometimes. So if you can go to the Part A, if you have that available for the MGS product, you can look on plate 5, and for each of those sand body units, there's a map in there that shows the depth that the aquifer is found at. So there's a little scale here that the light green would be depth of 0 to 50, this slightly darker green 51 to 100, yellow 101 to 150 feet. So we're looking for what can an aquifer be found at about 100 feet depth. So we're looking for an area or a figure on this figure on plate 5 from the MGS for where we have that kind of the line where we're seeing both this yellow and the dark green. And if you get to figure 5 for the HSA aquifer or the HSA sand body on that plate, you'll see that we have right where we're starting to see that yellow green border cropping up on this figure here. We have a little bit of yellow and green. That's showing that this is likely that the top of that sand unit that we're starting to see where your well is completed. So we've found that the likely aquifer our well is in is the HSA aquifer. You can also use the Part B if you don't have a Part A handy by looking at the cross sections. This isn't quite always as reliable because there's often quite a bit of space between the published cross section lines. But you can see on a map in the report that your cross section location is near, or your well is located near a cross section. In this case, it's pretty near cross section G. And then you can find a reference point along the cross-section line. So if it's by Highway 226, you can look in that general area. And using the elevations at the edge, so if we know the surface or the elevation here at the surface is about 1,500 feet, if you follow this across, and your wall's about 100 feet deep, you go down to 1,400 feet elevation, follow that back across, and you'll land again in this HSA sand body, this HSA aquifer here. So this does get a lot more difficult though if you're further away from these published cross-section lines. And in those situations, if you're digitally savvy and want to download all the Minnesota Geological Survey's digital geographic information system files, and you have the technology to do that, you can look at all the cross-section lines which are spaced 1 kilometer apart for the county. So you can find one that's much more accurately depicting the area where your well is located. So now that we know that our well is in that HSA aquifer, we can go to the stratigraphic column in the Part B atlas. This is figure 2 on pages 6 and 7 in the report. So when you start looking down through the legend here, and we look for HSA, and here it is. And we can then look at and see which part of the aquifer system, the upper or lower one it's part of in this atlas. So in this case, it falls in the area of this blue bar here. So it's part of the upper system of aquifers. We can see what potentiometric surface or groundwater flow map that this aquifer is represented by. In this case, it's going to be the map shown on figure 7. And then we can also see the pollution sensitivity figure that represents this aquifer, which is figure 22. So we can go to figure 7 then for the groundwater flow in that upper system of aquifers. And what direction is the groundwater flowing in the map here? Higher elevations are green or yellow, lower elevations are blue. Yep, it's moving downward or toward the south on this map. So in a broad sense, it's toward the south. And there's also, we can see a lot of those plus and X markers suggesting there's a lot of other nearby wells in the same upper aquifer system nearby to yet. And then we can go to figure 22 for pollution sensitivity for this aquifer. So on this figure, what's the major pollution sensitivity we're seeing in the circle? Again, red's very high, orange is high, yellow moderate, and then green's low and very low. Very, very high, correct. Yep. Very high sensitivity in the area. And we also can see that there's a sample from a well actually in the same general vicinity in this exact aquifer too yet. And it has modern tritium age water, so it's that post 1950s water, younger water. And it has a couple of numbers on it too yet. We see that black 5.93, which is evidence of anthropogenic or human introduced chloride. And we can see 2.27 in green, which is evidence of a potentially human introduced nitrate in the area as well. But there is no E on here, no red E, so there's no lake water influence in this general area that was noted in this particular sample, as there was in a couple other samples from this aquifer elsewhere by other lakes. You can see a lot of these same things again in that cross-section G on the plate 9. So again, here's your 100-foot deep well. You're in the HSA aquifer, all sand. It's got all those, there's no gray shading. It's all just the hatching and the polka dots and diagonals of different directions. That's all aquifers. Shaded pink for the younger post-1950s tritium water where tritium was found. And you can again see that one well sample right here where it's shaded in pink, where we found the tritium in that water sample, and also the same chloride and nitrate numbers you saw in that previous figure as well. Then there's a couple other things you can do with the water chemistry figures in the report. So in figures 11 and 12, which highlight that there's commonly anthropogenic chloride and nitrate in wells under 100 feet deep in the sandy southern part of the county, which is where this well is located. And then if you go to figure 13 on page 26 for arsenic, I also did a little cutout of that figure here on the left on the screen. This is showing that there are some arsenic detections in the area with these little orange dots. There was none detected though in the closest well to our site, so that one just has that black dot showing that it was below detection limit for the lab for arsenic in that well. But all the other ones in the nearby area, there are some samples of very in-depth 5 parts per billion, and none are in that big bright red circle here, showing that they were over the public drinking water standard in the vicinity. And then you also can use the plate 7 for the whole county to just get an idea again of what other nearby aquifer chemistry is available. So in the circle here, it looks like we just have that one sample we'd seen earlier, but there are other samples, especially over in like toward the west here in Park Rapids, toward the east up toward Beltane and Nevis, Spider Lake up that way. We're seeing other samples, water samples available to you in those areas, but in our general area here, there's not a whole lot else at different depths. You can also, again, look at permitted water use nearby. So in the general vicinity of the well here, within a couple miles, there is not a whole lot. There's a gray dot in there. That's an other use type, which in this case, it's just a bunch of the smaller uses that we lumped into the other category. And it's a sand and gravel washing facility there that was using water in 2020 for permitted use. But there are a few permitted users within a few miles elsewhere, with the greens and purples and blue dots, which are municipal irrigation or agricultural irrigation and golf course irrigation. And then just a reminder to you, in the back part of the report, you can check on the figures for nearby aquifer tests and nearby monitoring wells if those types of things interest you to yet, if you want to know more about the aquifer capacity to provide water or the water levels, if there's publicly available water level data from DNR monitoring wells. So with that, I'm just going to have a couple wrap up things here. First, there's going to be I want to mention that there's going to be a Wadena County workshop similar to this available. I think it's going to be just in person in this case. We're still working out the details, and I just got the date for that yesterday. It's scheduled for November 18th. So if anybody's interested in attending that, it'll be on November 18th. I think 1 to 4 p.m. at the Wadena County Courthouse in a meeting room there. And then also, if you are here in person, you probably grabbed a feedback form on the way in. If you would be willing to fill that out with your thoughts on today's workshop and presentation, that would be great. There's also an online form available at the link on the screen, or if you scan the QR code on the screen, you can fill out an online form. This is particularly relevant for you folks that are listening in online. If you would like to fill out a feedback form, you can use either of those options on the screen. So while you're filling those out, we have plenty of time here yet for questions. Looks like it's 3:18, about 10 minutes for questions before the scheduled end time. Anybody have any questions yet? Okay, we have a question here.
Yeah, I was wondering, what was the site again for the monitoring wells?
Yep, so yeah, the question was, what is the site to find the monitoring well information? So if you go on the onto a search engine online and just type in DNR groundwater, I think it's DNR cooperative groundwater monitoring, that should get you to the right page. Yep. Any other questions? Anything online, Susan? Okay, nothing in the chat.
I
Okay.
don't see anything online. The links you mentioned, I did put onto the chat. And
Okay.
I can email out later too.
Okay, perfect. Thanks, Crystal. Yeah, so I guess if nobody has any further questions, I just want to thank you all for attending today and for your interest in Hubbard County geology and groundwater. It's been a pleasure presenting this all to you all, and I hope you all learned something as well. If you have any questions afterwards, you can reach out to us. My email is on the feedback forms. If you take a picture of that ticket with you, Amy has hers available as well if needed. Or you can reach out to Vanessa Barada, my supervisor with the Atlas group too, if you have questions. She's also available. So
Well, thank you.
yeah, thank you again.
Yeah, thanks.
Okay. in the meeting.
I would also, the part A, I don't know where their original copies, but we did find the version online and
Yep.
hand print them. So I've shared them to my staff at Hubbard County SWCD. If anyone wants a printed copy, we'll print them and you can pick them up from us. So, and then we'll have the part B copies that we're looking at today on hand for anyone to pick up as well.
Okay. Alrighty, thanks. Have a good day, everyone.
Thank you.